Hey, all you calc cats. We're going to start chapter 6 today. Chapter 5 today. I'm going to try to condense it as much as possible, so let's dig right in and see what we can do. In the first section of chapter 5, we're talking about what they call an antiderivative, which is going to lead to an integral. And it's really important that you look at these things in the gold boxes that I put here. So how to rewrite some of the things algebraically so that you could get it into the best form in order to take your antiderivative or integral. Study these examples very, very carefully, examples 2 to 7 in section 5.1. You're also going to really rely on page 282, which is going to give you some of the integrals, all of the integrals that we'll be using, and how they relate to the derivatives that you already know. And then here's your homework assignment in these two sections, 5.1 and 5.4. I'll show you why we're not going to do 5.2 and 5.3 in just a minute. We're gonna go over it but not do it. So let's get right into it. The antiderivative here, let's say that this is our function. And this function is the derivative of f of x. And we want to know what was the original function that gave us this derivative. And this is a very, very important process, just as important as your derivative process and something that you'll be using in Calc 2 constantly. So what we want to do is, if normally when we took a derivative, we multiplied the exponent out front and reduced the exponent by 1, we're going to do exactly the opposite. So what we're going to do is we're going to add 1 to our exponent and divide by that new number. And do the same thing for this one. Add 1 to the exponent. It was a 1, now it's a 2, and divide by the new number. This one is really a 1x to the 0, so if we add 1, it's x to the 1 divided by 1 is just that. These will cancel out, and these will cancel out, and you'll see that what we get is, if we took the derivative of x to the third, we're going to get 3x squared, right? If we took the derivative of x squared, we're going to get 2x, and the derivative of x is 1. However, there could have been a constant here added to this original function that we wouldn't see in the derivative because the derivative of the constant is 0, so it wouldn't show up in the derivative of f of x. So that's basically the process. Sometimes it's hard to get it into a form where you could take the derivative of it. That's why I want you to rely on page 282 a lot, and also these examples to show you how to rewrite them. Now, this one I'm asking myself, the derivative of what gives me sine? Well, the derivative of cosine gives me a negative sign. So therefore, the derivative, the antiderivative of the sine of x should be a negative cosine. Now think about it. If we were to take the derivative this way, it would be a negative sign, which brings us back to this. Again, it could be plus some kind of constant, just in case there's a constant added to this original function that turned to 0 when we took the derivative of it. So think your way through this one. Look at page 282. So again, the derivative of the cosine is a negative sign. And then a negative sign is what gives us the positive sign. So sometimes you have to have a little bit of insight into what would make this derivative from what function. What we'll also see is this, what we call an integral symbol, which is like an elongated S, which stands for summation. We're going to talk about another summation in a minute, but this is a summation or an integral sign. And this says that I could do both of these separately, plus s squared, the secant squared theta. And what is this d theta if I could distribute it into both of these? This d theta is if theta is a function of something else, we then, according to the chain rule, we would have taken the derivative of that theta, whatever it was, and we would have gotten a d theta. It could be d theta dx or whatever, but if we do our antiderivative here, what we're going to get is we're going to get a theta to the third over 3, then plus, and then we say to ourselves, Well, the derivative of what gives me a secant squared? And if you remember, the derivative of the tangent is secant squared. So this would just be a tangent theta. And again, plus c. Because it could be some constant added onto that original function. Now, if we take the derivative of this, it's going to go back to 3 out front, reduce the exponent to 2. The 3's cancel out. We get a theta squared. Derivative of tangent is secant times the derivative wherever theta was. When we're going back, this actually gets assumed back into the original function. So when we take the derivative of this one, we're going to get this times the derivative of whatever theta is. So that's where that d theta comes in. And we're going to see that more and more, like this one has a dx. This one we can't take the integral or antiderivative of in the form that it's in. So we're going to rewrite it, and we're going to write x to the 1/2 power. I'll distribute this dx. This really should be like this. Plus, I'm going to bring this x to the 1/2 power up and make it x to the -1/2, and then a dx on that one. So I don't always write this step because I just understand that it's both of these separately. It equals this. The other thing that the book will show you in its examples, it will rewrite this like this, x dx, and they'll move this 1/2 out front. So when you have a constant, you're allowed to move it out front of the integral. So if I take the derivative of this, or the antiderivative of this, I'm going to add 1. 1 plus 1/2 is 1/2, which is 3/2, and divide by that new exponent. And if I divide by a 3/2, it's the same as multiplying by a 2/3. So this is going to be plus 1/2, and I'm going to add 1 to this. 1 plus a -1/2 is a positive 1/2. Divide it by a 1/2, which is the same thing as multiplying by 2/1. So I'm going to get a 2/3 x to the 3/2. The 2's will cancel out, and I'll get an x to the 1/2 plus c, some constant. It could have been plus 5. We don't know what it is, but when we take the derivative of it, it becomes a 0. Now looking at this number 36 off to the side here, they may say, well, here's your derivative. Find the constant. What would the constant be? This is like number 36 in your book. So if they're giving us a hint that when they put 0 into the original function, they get an 8 out. So if I take the antiderivative, squared, divide by 2, I'm going to get a 5x squared. Add 1 to this, it's 4. Divide it by 4, I'm going to get a 3x to the 4th plus some constant. If you have to pause your video to look at these again, do that and study them very carefully, and then start the video again. Here's the clue they gave me. So this is basically my original function, except that I don't know what c is. If I put a 0 into this function, it tells me that c is equal to 8. These 3 dots again means therefore. So if f of 0 comes out to this, c equals 8, so then c equals 8. You might have another number over here, and you'd have to subtract from both sides or add it to both sides or whatever in order to get c. But look at this one again very carefully. Another summation notation, which we're not going to get into too much, but you will see it in Calc 2, because when they do infinite series, you'll see this notation. This is sigma notation. Sigma notation very simply says that your starting number is I, the ending number is n. And this tells I'm going to add up n terms according to the function that they give us. Well, they're giving us just this a. We don't know what it is, but what this notation says is we're going to add up the first term, second term, third term, all the way up to the nth term. If they give us this, this means, oh, I'm putting a 1 in for I and getting a 1, then putting a 2, all the integers, getting a 2, 3, so forth, all the way up to 10, and I'm going to add them up. There's certain formulas for this, but let's see, this 3i squared says if I put a 1 in, I get a 3. If I put a 2 in, I get 2 squared, which is 4 times 3. The second term would be a 12. The third term, if I put a 3 in here, I get a 9. 9 times 3, that's where I get my 27, and so forth. If I put a 9 in here, I'm getting 9 squared is 81. 81 times 3 is 243. That would be my 9th term, and so forth. And then I would add these up. This is summation notation. There's formulas for this on page 291, which work really nicely. I don't know if it was Galileo or Gauss, when they were a child in elementary school, they were so smart and their teacher gave them a problem to add up the numbers from 1 to 1,000, just to try to keep him busy because he was so unbelievably intelligent. And what this mathematician did, I think it was Galileo, he came up with the answer immediately, which was 500, 500. It says 500,500. And what he actually did is he took the first and the last one and noticed that they equaled 1,001. And then he noticed that the second term and the second to the last term, if he added them together, they also equaled 1,001. Same thing with this one. They also equal 1,001. So there was actually 500 pairs of 1,001. And when you multiply that together, you get a total of this. This brings us to our formulas, which one of the formulas for adding this up here is going to be n times n plus 1 divided by 2. And if you think about it, if n was 1,000 in this case, we're going to get 1,000 times 1,001 divided by 2. That's where the 500 comes from, and that gets us the sum. On page 291, there are 4 or 5 of these formulas that were figured out over the years. So to simplify some of these, like this one, it says the sum of 4i from 1 to 24. So this would mean 4 plus 8 plus 12. Put a 4 in there, we get 16, all the way up to 4 times 24 and add them up. But this formula does something for us, this formula right here, which is found on page 291. It does the math for us. When we put 24 in here, we get 24 times 25 divided by 2, and then times the 4 comes out to 1,200. We could do the same thing. This is actually number 20 in your book. From 1 to 25, they're saying it's I to the third minus 2i. If we put the first number in, we're going to get an I minus 2. Put the second number in, we're going to get an 8 minus 4. And if we listed those and did all 25 terms and added them up, it would come out to be this. This is how. We separate this into two terms and move the constant out front. We take the formula for I to the third, which is found on page 291, and we substitute a 25 in there. And then we take the formula for the I, which is found on 291, and we put a 25 in there and do the arithmetic, and we get this. Check this out and look at it over and over again. We're at the 13-minute mark, so I'm going to post a second video, which is going to be on areas. So look out for that one.